So this is where we begin our so-called syllabus for class 11 12, where we will start with a section called vectors. So before we come into vectors, we will talk a little bit about physical quantities and their importance in physics. Okay? So because vectors is nothing but a classification of physical quantities. So vector kya hota hai? It is a special type of physical quantity which has certain properties which we will discuss. Okay? So first of all, if we think in terms of physics and all physical quantities involved in physics. So you know that whatever branch of physics that we are studying, whether we are studying mechanics where we deal with things like forces, accelerations, velocity, momenta, torque, angular momentum, things like this, or we are dealing with, let us say, electricity and magnetism where we are talking about things like voltage, electric current, magnetic field, magnetic force, things like that, or we are dealing with electrostatics, which is to do with static charge, and the force and field created by static charge, like electric field, electric forces, etc. Or we are talking about some other branch of physics like thermodynamics and heat, where we are talking about thermal energy, we're talking about temperature, we're talking about conductivity, thermal conductivity, we're talking about radiation pressure, things like that. Whichever branch of physics we're dealing with, ultimately we are always talking about different physical quantities and how they interact with each other. So for example, how force is related with momentum of a body, that the net force acting on the body equals the rate of change of momentum, or how velocity is related with acceleration, that velocity, acceleration is defined as the rate of change of velocity. Or for example, how the amount of temperature change in a body might be related to both the heat supplied as well as the mass of the body. Q is equal to ms delta theta, that formula that you might have studied, that the heat supplied to a body is directly proportional to the temperature change and is proportional through the mass and a property called specific heat capacity, etc. So whatever laws of physics that we study, we are always concerned with how different physical quantities interact with each other in physics. We are never concerned with non-physical quantities. So what are non-physical quantities versus what are physical quantities? Let's try to understand that. So a definition of a physical quantity, kya hota hai physical quantity? It is any quantity that can be measured. Okay? So anything that can be measured, we refer to as a physical quantity. So whether we are talking about length, mass, time, force, okay, momentum, kinetic energy, okay, potential energy, heat, temperature. Yeah, I mean, Prince, just to answer your query, Prince has sent me a query here that whether you need to make extensive notes of all this. You just treat this like a regular lecture. So I will give you sufficient time, after explaining each thing, to note down the important points from what I'm teaching on the board. And yeah, definitely you should maintain a separate notebook for your vectors, or at least one notebook for your physics, if not separately for vectors. And you should have the classwork as well as the homework problems, etc., done in that notebook. And you should have your own class notes. Now, how detailed your class notes should be, that really depends on you, because you don't need to write each and everything in a lot of detail, especially because I'll be sharing the PDF of these whiteboard notes with you. But the reason why you should be noting down things is because it's a very common thing for all of us that when we write down something, it gets ingrained in our memory better, and our understanding of it also improves. So rather than only hearing and responding that way to what I'm saying, if you also keep jotting down the important points, and especially when we come to some of these sums and the numerical problems, I'll be solving some sums on the board here with all the steps. So if you note down those sums with the steps involved, then you'll see that your learning will improve accordingly. So yes, you should have a notebook and you should have a pen, and you should keep noting down the class notes. Again, as how much detail you write down the class notes in is really a matter of your preference. But as far as I'm concerned, what is of course important is the definitions, the formulae, and the most important thing, when we are going to do applications of formulae in certain questions on the board over here, then each and every step of those questions, it is preferable if you note them down. That will mean that your learning in the class is that much better. So you should do that. Right. So moving on now. So we are talking about all various types of physical quantities. Let's take some more examples of physical quantities. So you have heat, temperature, things like that. You have displacement. You have force. You have electric field, magnetic field, okay, etc. So many different physical quantities. So how do we say that okay, a given quantity can be classified as a physical quantity? अगर हम उसको measure कर सकते हैं, okay, so anything that can be measured, that is classified as a physical quantity. So the side note of that becomes that okay, what is a non-physical quantity? So non-physical quantity is something that cannot be measured, and that's not really important for us in physics. In physics, we are always dealing only with physical quantities. So non-physical quantity, so to speak, just in terms of general knowledge. So non-physical quantity would be something that cannot be measured. So anything that cannot be measured. Okay. For example, you can say that the sadness of a person or the happiness of a person cannot necessarily be measured. Okay, you can maybe compare that. Okay, one person is happier than the other, one person is sadder than the other, but you cannot really measure it. Okay, or if we say that the emotions, so all these kind of things which will never really come up for us in physics. So the physical quantities are only quantities which can be measured, and they are the things which are important for us in physics. Okay, now further we will see that on the basis of their properties we divide physical quantities. So that second part is not so important. That was just to give you an example कि non-physical quantity भी होता है कि नहीं होता है तो क्या होता है उसका definition क्यों होता है. So that is just to explain that. So anything that cannot be measured, you can say doesn't come in the domain of physical quantities. So you can just say simply that अगर हम उसको measure नहीं कर सकते, we don't need to bother about it in physics. We study some other subject later like philosophy or psychology or something, we might be worried about it. But in physics, we are not concerned with it. So we are only concerned with quantities that can be measured. Now on the basis of that, we will see that further physical quantities we classify into two categories. We classify physical quantities into something called scalars and vectors. And scalars is something that we are familiar with till date. Vectors is probably new to most of us. Okay. So our entire chapter today and from this point onwards, the first section of physics is about vectors. So what are scalars? They are physical quantities which have just magnitude. Or you can say they are physical quantities which are defined by a magnitude. And you might ask, okay, what is a magnitude exactly? It is just a magnitude is just amount of quantity. Okay. It is the amount or quantity of. So for example, we define mass as a scalar quantity. Because when we are expressing any mass, we just express it as mass is 2 kilograms or 500 grams. So it is just a measurement of the quantity of mass or the what we call the magnitude of mass. That's what we mean by it. Okay. So similarly, another example of a scalar quantity is time. We might say time is 2 hours, or we might say it is 31 seconds or something like that. Okay. Similarly, another example of a scalar quantity could be something like, let's say, distance traveled. Okay, so we might say that the distance traveled is 500 meters, okay, or 12 feet, or any such thing. So it's just a quantity. Okay. Similarly, we can say speed. Okay. The speed is, let's say, 18 kilometers per hour, okay, or any such thing. So we can see. Okay. So don't confuse this thing. This is a separate amount of mass. Okay. So we are saying that mass is, we might say as an example, mass is 500 grams. Or we might say that, okay, another mass is there, M2, let us say, which is 500 grams. M1 is 2 kg. time t1 is 2 hours, whereas let's say another time t2 is 31 seconds or something like that. Okay, so you can see that whenever we are expressing some measurement over here, we are just expressing it, or whenever we are expressing the physical quantity, we're just expressing it in terms of the amount of that quantity or the magnitude of that quantity. Whereas, so this is something that all of us are familiar with, nothing surprising there. But when we come to the more interesting, we're learning today vectors. In vectors, we will see that they are physical quantities which are defined by, so vectors are that are defined by a magnitude and, very importantly, that is not enough to define it, and a direction. They have a particular direction along which they act. Okay. So by magnitude, again, we mean amount or quantity. But by direction, we mean that it has a line of action. Okay. That is, it acts along a particular line. So that quantity is called the direction of it. Okay. And you will realize from the moment we take these examples why the direction becomes important. So the best example of it is something displacement. Because displacement is defined as the shortest path from the initial position to the final position. So if I just tell you that somebody's displacement is 5 kilometers, it is not enough. I have to express which direction is it. Is it 5 kilometers towards south? Is it 5 kilometers towards northeast? Is it 5 kilometers vertically upward straight, or 5 kilometers vertically down a tunnel into the earth? Only when I give the information about both magnitude and direction, then the information about displacement is complete. Similarly, we'll see later that force is a vector quantity. Okay. At a later stage in class 12, we will see electric field is a vector quantity. But on the other hand, energy is a scalar quantity. Okay. So there are quantities which are defined in terms of both magnitude and direction, and such quantities are called vector quantities. Whereas on the other hand, there are quantities which are defined only on the basis of their amount or the magnitude, and such quantities are called scalar quantities. So for example, when we express a vector quantity here, we might express it as the displacement of a body is 10 kilometers towards north. So you can see that when I'm defining a certain amount of displacement, there are two pieces of information जो जरूरी हो जाते हैं. एक कि how much the amount of that displacement is, or what we call the magnitude of the displacement. The other is also the direction in which that displacement is acting, which is in this example towards north. So both the informations are critical. Otherwise, I cannot define the displacement. So therefore, displacement is which kind of quantity? It comes in the category of vectors. Yes, distance is a scalar vector, whereas displacement is a vector, and that you will see is as per the definition of distance and displacement. Distance का definition क्या होता है? It is just the amount of path, okay, or it is what we call the path length. So for example, if you go around a full circle and come back to where you started, you would say your distance covered is equal to the circumference 2 pi r, but our displacement will not be 2 pi r, it will be c. Okay. So that is where there is a clear difference between the quantity displacement and distance. Okay, so hope this point is clear to all of you. So just make a note of this, a brief note if you want, and you'll understand some more examples. So the last example, the displacement I have said is like this. It is expressed both in terms of a magnitude and a direction. Whereas when I express a distance, I don't need to give any direction. Yes, Dushyant, to answer your question, momentum we will study later in physics is defined as a vector quantity, because momentum is defined as mass into velocity. And we will very soon learn that velocity is a vector quantity. Velocity comes in the category of vector, whereas speed comes in the category of scalar that we've already seen. Speed comes in the category, but momentum is not defined as mass into speed. Momentum is defined as mass into velocity. So in fact, because it is defined as proportional to the velocity, therefore it has direction, because velocity also has direction. And further later we'll understand why velocity has direction, because velocity in turn, how do we define velocity? We define it in terms of displacement. We say velocity is rate of change of displacement. So because displacement is defined by its direction also, so accordingly velocity also gets defined by the direction. Okay. So as a simple example, we can see something like this, that I mean, this will become more like a kinematics example actually, but you see that suppose we have a system of axis where this is pointing towards north, okay, and this direction here is pointing towards east. So this is west and this is south. So in this horizontal plane, suppose I'm having a situation like this, where let us say a certain body it covers a path which is along a circular track. So a certain body. So suppose what happens is that our body, in fact, or a particle or whatever, suppose it started from here, from this position here. Let's say that position is E. It started at time t equal to, let's say, 12:30 p.m. It started from here and it went along this circular path, okay, and it reached this position here, let's say B, okay, at, let us say, a time of something, let's say 12:45 p.m. And this here is basically, let's say, it's a circular path of radius equal to 12 meters. This is the information. Now, from this information given, if I ask you, express the distance covered and the displacement. Okay. And secondly, I ask you that find the average speed and find the average velocity. So the moment we sit down to calculate these things, it will make it even more clear for us that what is the difference between vector quantities and scalar quantities. Okay. So just on the basis of definition, you know from your background knowledge of class 9 that distance, हम कैसे define करते हैं? It is a scalar quantity which is defined as path length. Okay. Whereas displacement को हम कैसे define करते हैं? Displacement is a vector quantity and it is defined as the straight line from the initial position to the final position. So with this background information in mind, okay, now what I want you to do is first of all get this part, the E part of the question. So this is an example we do. And in our compass, actually, this line is pointing towards north. And this line here is pointing towards west. So that is our reference. This is pointing towards east. And so on and so forth. Okay. So using this reference and using this diagram, and of course, given the fact that radius is 12 meters and all that, we have to first calculate distance and displacement. And next we will talk about average speed and average velocity. Yes, Anmol, that is correct. But the thing is, Anmol, only one thing, that when you are expressing the displacement, you have to also give me the direction. Just the information about so many meters is not enough. Now you have to also express the displacement in terms of the complete definition, in which you have to tell me the direction of the displacement also. Okay, Ian, I'll just show you the definitions once again. Let me finish with this part, and Khushi, to answer your doubt, yes, acceleration is also a vector quantity. Yes, Dushyant, your answer is correct now fully. Elian, your answer is also correct. Anmol, correct. Okay. Yes, correct. Khushi, your answer is correct. So here, what I'll see is that the distance traveled, okay, since it is defined as the path length. So that is, we can see it is 3/4 of the circumference of the circle. That was clear to us from the diagram. So it is 3/4 times 2 pi r, where r was 12 meters. Okay. So this will become how much finally? This will become 18 pi meters, or approximately 18 into 3.14. Okay. Whatever that works out to be in meters. So that is as far as the distance is concerned. But as far as the displacement is concerned, okay, the displacement is defined as the shortest path, or basically it is the straight line from initial to the final position. Okay. So if I go back to my diagram and I work that out, okay. For example, in this diagram, let me just pick up the diagram. So you see in this diagram, this is my initial position. This is where we started from, and this is my final position. So I have to now express my displacement as this one. This arrow here will represent my displacement. This becomes, in my diagram, the displacement. And as you can see that in this triangle, this side is equal to this side. So that's the radius each. Okay. So this angle will be 45, as will this angle be. So you can see that as far as the vector nature of that displacement is concerned, now we can say that the displacement is r root 2, okay, towards which direction? Northeast. Because you can see how this displacement arrow is pointing. It is pointing in this sort of a direction. The displacement arrow is pointing such that it is bisecting the eastern direction and the northern direction exactly. This angle is 45 degrees and its length is r root. Okay. So that r root 2 is approximately 12 into 1.41 meters. Okay. But more importantly, when I express the displacement, I have to give information about both direction and magnitude. Just giving that it's r root 2 is not enough. I have to also express the direction. Okay, people, so hope this example is clear to all of you. So I'm just minimizing this a little so that you can go through it in detail and understand distance and displacement properly. Okay, people, so hope this is 100% clear. Everything, yes. Just going through your messages, but don't think I have any doubt. Yeah. Yeah, I'll just take you to the definitions again. So just on request of a couple of students, I'm actually going back to the earlier section. We'll come back to this question and we'll come back to the second part where you have to find out the average speed and average velocity. So those who might have completed the first part and writing it down and all that, you can continue with the second part of the question. Whereas on request of some students, I'm just taking you through the slide of the definition of vector and scalar quantities again. This is that definition. Okay, so physical quantities that are defined by both a magnitude and a direction. Okay. By direction, we mean the line of action along which they act. By magnitude, we mean the amount or the quantity of the material, of the quantity, physical quantity. Okay. So that is called a vector quantity, whereas a scalar quantity only has magnitude. It does not have any significant direction. Right. And now coming back to this question. So now work on the second part of the question. Yes, so I'll explain the second part. Okay. So now we are going back to for the first part, you have to calculate distance. Now distance को हम कैसे define करते हैं? We define it this way, that it is the actual path length. So in this case, you can see that he is covering 3/4 of the circle. So the actual path length comes from that. But displacement को कैसे define करते हैं? It is the shortest path from initial to final position. So in other words, it's a straight line from the initial to final position. So in this particular case, where he is at the initial time, 12:30 p.m., he's at the point A. Where is he at the final time, which is 12:45 p.m.? He's at B. So the displacement will be defined as the shortest path from A to B. In other words, it will be a straight line from A to B and always pointing in which direction? From the initial direction to the final direction. So that is why we have expressed the displacement in this diagram below as this. What we simply do is we draw a straight line joining the initial and final position, and also the direction is pointing from initial position A to final position B. So once we do that, we can see it is actually a chord of this circle, which is actually subtending 90 degrees, because 3/4 circle is the distance he covered. So his displacement will be the line joining these 2 points, which will be a chord subtending 90 degrees at the center. So now you're using your normal geometry, that this becomes an isosceles right angle triangle, which is why the chord length, that is the magnitude of the displacement, is nothing but the chord length, which is r. Whereas what about the direction? So for the direction, you can see the arrow is pointing from A to B. So it is pointing in which direction? 45 degrees it's cutting, it's bisecting the northeastern direction by 45 degrees. If you see, this is the initial position A, and this is where he's ending up over here B, let's say. So from A, he's not going north, he's not going east, but he's going in a direction which exactly bisects that northeast direction. So that is why we call it northeast, or 45 degrees north of east, like that. So this becomes the distance and displacement. Now for the B part, we talk about average speed, and we talk about average velocity. These 2 things. Okay. So the average speed will be defined as total distance divided by total time. So in this case, the distance was 3/4 of 2 pi r divided by the time. Now the time will be how much? It is 12:30 to 12:45 p.m. So it is 15 minutes or 900 seconds. Okay. So this will become 18 pi meters divided by 900 seconds. You can see it is pi by 50 meters per second. So that is approximately 0.031, sorry, 0.06. Taking pi as 3.14. Okay. So this becomes your average speed. Okay, so hope this is clear. The first part, the average speed. Because remember, the radius was 12 meters. Okay. Now, likewise, if you talk about the average velocity now, so average velocity क्या हो जाएगा? It is defined as displacement upon time. So the displacement was how much? It was r root 2 towards northeast. So I'm just writing that in short form. Okay, divided by the time interval. So this is 12 into 1.41 divided by 900 meters per second. But again, its direction will be towards northeast. Okay, so we can complete this calculation. So roughly, but more importantly, towards northeast. So the velocity, like the displacement, is defined by both the magnitude and the direction. Okay, hope this example is clear. Okay, now let's look at another example to understand the difference between scalars and vectors. So another example like this, that in one case, we're having, let's say, initially a container. So this has, let's say, 500 milliliters of water are present in the container. Okay. Now, another 200 milliliters of water are added to the jar or container. So find the total volume of water. So that's situation 1. But in situation 2, let us say, let's say a person called Amit, okay, makes a displacement of 12 kilometers from 1 to 1:30 p.m. Makes a displacement of this much from 1 to 1:30 p.m. and a further displacement of, let us say, 16 kilometers from 1:30 to 2 p.m. So find Amit's total displacement from 1 to 2 p.m. Now consider this question, and through this you will understand what is the vital difference between scalar quantities and vector quantities. In one case, you had a jar with certain amount of volume of liquid, and you added a volume of liquid to it, and you asked what is the new total amount of volume, or what is the net volume that you're getting in the jar after you added that second piece of, or that second volume of water to it. But in the second case, you are not adding volumes of liquid. You are rather adding two displacements. Okay. So see how you will deal with each part. Exactly. We cannot be sure. So that is the whole problem. So you have got the question correctly, Anmol, that in the second part, we actually cannot answer the question. We have insufficient information. We don't know what the total displacement will be because there's no information given about direction. So that was the whole point of the second question, that if I don't have the direction, then actually I don't have the definition of displacement. उसका कितना डिस्प्लेसमेंट हुआ है वो उसका उसका डेफिनेशन मेरे लिए कंप्लीट ही नहीं है. ये जो 12 किलोमीटर्स है और जो 16 किलोमीटर्स है, दैट इज हाफ इंफॉर्मेशन, दैट इज नॉट कंप्लीट इंफॉर्मेशन. सो विदाउट द कंप्लीट इंफॉर्मेशन I cannot understand what the total displacement is, and that is why displacement is a vector quantity, whereas volume is a scalar quantity. Because to add two volumes, I did not need to have any information about any sort of direction. But to add two displacements without the information about direction, I am left with nothing. Okay. So the solution of this, or you can say the explanation of this whole scenario, is that in case A, the total volume is just the initial volume, let's say V1, plus the volume we added, that is 500 plus 200 in milliliters. So the final total volume that we are getting is 700 milliliters. Okay. And this is something very obvious. You might ask that why we are even doing this over here. But the thing is, what we have done here in terms of operation is that we have done what is called a scalar addition. Scalar addition was performed. Why? Because volume is a scalar quantity. But for the second information which I have given, you have to now find the net displacement. So you can see that it actually cannot be calculated. This cannot be understood because there is no information about direction. So that becomes a very critical thing. Without the information about direction, displacement being a vector quantity, if I don't have information about the direction, it's useless information. I cannot do anything with the displacements. Okay. So that becomes the explanation of just this standalone question. Okay. Now we'll see that, okay, if we give some information about direction of the displacements in the question, then maybe we can resolve the second one. Maybe we can resolve it then. Okay. So we'll do it that way now. So let's see another version of this second part. Now let's say we got a C part. Now suppose displacement S1 is 12 kilometers. Yeah, don't worry, I'll show you in there. Okay. So displacement S1 is 12 kilometers towards north. Okay. And displacement S2, that is equal to 16 kilometers towards east. Okay. And this was obviously whatever 1 to 130. That same thing as the previous one. Now I ask you, find the net displacement from 1 to 2 p.m. Now you can see that the question at least makes sense. Okay. You might still have to do a lot of steps before we can get the final displacement, but the question makes sense. In the previous part, it did not make sense only because we cannot understand only what is the net displacement because there's no information about direction. But the moment I give you a fresh question where there's some information about the individual directions, okay, we are able to get. And yes, Kushal, your answer is correct. Good. Yes, Anmol, your answer is correct. Alian, your answer is also correct. Uday, very good. So all of you are getting the answer to this. Okay. Yes, Aditya, that's correct. Akshat, correct. Okay, so now we can see that if we try to visualize this third problem, we end up with something like this. Okay, what we'll understand is in the third problem, let us say the person first made a displacement of 12 kilometers towards north. So if I assume that in my paper, I've kept my piece of paper or whiteboard or whatever, such that the above y-axis is representing north again, okay, and it is expressing east, west, south, etc. Then I can show that, let's say this point was A and this point was B. So A to B is my initial displacement, which is 12 kilometers towards north. So A is where he was at 1 p.m. and B is where he reached at 1:30 p.m. So I can see that the first displacement I can represent as AB. So A to B, that actually represents displacement S1, which is 12 kilometers towards north. Okay. Now my second displacement is, let us say, B to C, which is going to be how much? It is going to be 16 kilometers towards east. Right? That is what the information was given to me. That it's 16 kilometers towards east. So coming back here, in this diagram, when he makes that second displacement, where would he end up? He would end up somewhere here. From this point B, he would go 16 kilometers but towards east. So he would, for that second interval of time, his displacement would look like this. It would be 16 kilometers in magnitude, but it would take him to a point C, which is now located over here. So from this point B, he is going to the point C, and he's reaching that point at precisely 2 p.m. Okay. And the angle between these two is 90 degrees because this is towards east and this is towards north. So now we can see that by definition in this diagram, how would I express my net displacement? My net displacement from 1 p.m. to 2 p.m. would be the shortest path from 1 to 2. So it would be this. This vector or this straight line now actually expresses my net displacement. Let us say that is S net. These were S1 and S2. Okay. Now what we can do is you can make use of Pythagoras theorem and you can see that the net displacement's magnitude will be square root of 12 square plus 16 square by Pythagoras theorem. That will be 20 kilometers. Okay. And its direction is somewhere towards northeast. Now, it's not exactly 45 degrees because you can see that this angle. So I'll talk about this angle at a later stage also. We'll see that interestingly that one of the angles in this triangle will be 37 degrees and another angle in this triangle will be 53 degrees. So we can also give complete information about the direction from that information. Okay. So in this triangle, suppose this angle is is theta. Now we don't know theta just now, but we can see that. So the net displacement, will be 20 kilometers, okay, along a direction which is at theta degrees east of north. So we still have to find out how much that theta is, but once we find out that angle in degrees, we can also express the direction in terms of an angle. Now, why I'm calling it east of north is because, see, the angle theta that I made in the diagram, it is like this, that this is your north wala direction, this is your east wala direction. और मैंने जो net displacement वाला vector draw किया है, this green colored arrow, that is basically doing what? It is, you're rotating from the northern direction towards the eastern direction. So you would have taken an arrow like this, but now you're rotated it towards the eastern direction by a certain angle. So that angle is theta. So that is why I'm expressing it as theta degrees east of north, because this arrow is going from north towards east. And this angle theta is rotating that displacement arrow from the north towards east. So we'll express it as theta north of east. Okay. Now I'll just come to the value of theta in a moment, but just write this much down first. Yeah, so we can't really say northeast, because northeast का मतलब क्या होता है? If I don't give any angle and I just say northeast, that means I'm taking it as that by default it is 45 degrees. It's exactly bisecting north and east direction. If I just say northeast without any angle, it actually means that I'm talking about the bisector of the northeast direction. So that should be at 45 degrees. Whereas you can see here, this is not going to be 45, because this is not an isosceles right angle triangle. Okay, so hope it is clear to this step. Okay, now I'm just going to give you the angle here and I'll explain that in a bit of time. Okay. So just write this as an additional note here, that the angle theta will actually be equal to 53 degrees. Okay. Now why this is the case, I will explain. So the explanation of this comes later. It comes in a bit of time. I'll just explain. But you know, from the diagram also you can kind of make out that ये angle जितना भी है 45 से तो ज़्यादा होगा, because this side is 16 and this side is 12. So if you look at this triangle, it's kind of like this. This side is 12, this side is 16, this side is 12, and this side is 20. So you can kind of understand that theta has to be more than 45, because a 45 on a triangle would have looked like this. In comparison, draw a 45-degree right angle triangle, it would have looked like this one, where this side is 12, this side is 12, and this side is 12 root 2. So you can see this side is stretched a little bit more. Na? यहाँ से यहाँ कहीं stretch हो गया. So this angle is getting stretched more than 45 degrees. Okay. So we'll come to that explanation. Why the value is exactly 53 degrees, we'll come to that. Okay. So when I'm describing the displacement over here, the complete answer is not sufficient to say that it is 20 kilometers. We have to give the direction also. So this angle is very critical. We have to say that it is 53 degrees east of north. Then my definition of the net displacement is complete. Okay. So when we discuss some common right angle triangles and trigonometric ratios for them, I will explain to you, how I got that value as 53. Okay, so hope this example is clear so far. Yeah, Anmol, very correct. You can write it as tan inverse of 4 by 3. And if you use a calculator or something like that, a real calculator, that is a scientific calculator, it will show you a value which is approximately 53 degrees. Or if you have one of those log tables at home which also have the trigonometric tables, you can look up the value of tan 53 or cos 53 or sin 53, and from that right angle triangle you can work it out. So I'm coming to that explanation very soon. Right, so now suppose I had another situation in this same thing. I had a question where it was actually something like this one. Suppose I had that S1 was 12 kilometers towards north in the same question. But instead of S2 being 60 kilometers towards east, suppose S2 was 16 kilometers towards south. Okay. So now can you tell me what is the net displacement? Now, this is again 1 to 1:30 p.m. Yes, very good. Correct. Anmol, that's correct. Yes, Aravinda, that's correct. Prince, correct. Getting a lot of correct answers. Dushyant, correct. Nishchal, correct. Uday, correct. Divyam, correct. Okay. So I might miss out somebody's name. Don't feel bad, okay? Because it's a little difficult for me. The messages coming out continuously to get everybody's name. So yeah, Sneha, Rishit, Anmol, Rimjim, Aditya. Okay, Dushyant, all of you got the correct answer. So when we are calculating the net displacement now from 1 to 2 p.m., you follow the same kind of logic, but here the directions are becoming different. So what is happening is he is first going like this, let's say A to B towards north, 12 kilometers. So he's going from the point E where he started to this point B, where he's now there at 1:30 p.m. He started from A at 1 p.m. अभी next case में क्या कर रहा है यहाँ पे? Our previous person was rotating by 90 degrees and going like this 16 kilometers, but this guy is taking a U-turn. He's going towards south now, so he's going like this now. So just for the sake of this thing, so that we can see it in the diagram, I draw this slightly parallel. Okay. But you have to understand that these lines are actually overlapping. Okay. So now he's making a displacement of 16 kilometers towards south, and he's ending up in his final position, which is this point C, let us say, at 2 p.m. So now I want to calculate the net displacement. So the net displacement is what? It is the displacement from 1 p.m. to 2 p.m. So it is the line joining A with C. So you see that the net displacement is this arrow. This one. Okay. So that one is my net displacement, wherever that is gone. So you can see that because this is 12 and this is 16, this net displacement will be 4 kilometers and its direction is towards south. Okay. So you can see something interesting, that you made a displacement of 12 followed by 16, but your net displacement was actually the difference of the two. It was 16 minus 12, 4. So through these examples, you see how vitally important the direction is in a vector quantity, because we cannot do any operation on a vector quantity without having information about direction. Okay. So through this, basically, we have understood the definition of vectors and scalars, and how vectors are very different from scalar quantities as far as their operations are concerned. When we combine vectors, similarly later we'll see when we do other type of operations like subtracting vectors, etc. Also, the way the algebra is done is very different to how we do for scalars. Okay. So with this, you can say we've got a sort of introduction to vectors. Now we will start with our further understanding of vectors. So the first thing we'll understand is symbols. What kind of mathematical symbols we use when we are dealing with vectors. So any letter with an arrow on top, it is understood that it is a vector quantity denoted with a symbol capital E. So for example, we might define displacement just to show that it is a vector quantity. We'll define it as the standard symbol S that we use, but with an arrow on top. Okay. We might define force with a symbol capital F, but from now onwards, with the capital F, we'll put an arrow on top because we understand that it's a vector. Whereas, for example, if we define mass, we just use the symbol M because it's a scalar quantity. But if we define displacement, we understand it's a vector quantity. So in our symbol, to show that it's a vector quantity, we put an arrow on top of the alphabet. Whatever alphabet we are using to define that quantity, we put an arrow on top of it. So arrow on top of it means that it is read as a vector quantity. Okay. So that's the first thing. Now the second thing is, if you want to just define the magnitude of the vector, then we use the modulus symbol. So this symbol, even though in mathematics it is read as modulus, but in vectors it is read as, it is the magnitude of the vector E. So for example, if we want to express that the magnitude of a force F is 50 newtons, suppose. So in mathematical language, now we'll express it like this, that the vector force has a magnitude of whatever, 50 newtons. This will be the correct way to represent the above information, that the magnitude of the force F is 50 newtons. Okay. If we write like this, that capital F vector is 50 newtons, this is not a correct statement. This is a wrong statement, because the left hand side of the equation is a vector and the right hand side of the equation is a scalar quantity. It is just a number and a unit. So we cannot equate a vector quantity with a scalar. That's why we have to put it in the modulus. Okay, so the modulus or magnitude of any vector is a scalar quantity, because it is just the magnitude of the vector. It's just the quantity without the direction. So just leaving you to note down the two symbols that we discussed so far. Okay. Yeah, please. This is just about the symbol. Okay, so that we understand that, okay, we use a symbol like just x. We understand that it represents a scalar quantity. But if we put the symbol x with an arrow on top, now we understand that it represents a vector quantity. And further, if I'm talking about just the magnitude of that vector, then we put it in the modulus sign. So this is now the magnitude of the vector x. Whereas this is the vector x, this is the scalar quantity x. Right, so this is fully clear. This is just about symbol. It's like about nomenclature. You haven't really learned anything from it. Yeah, then it is correct. If you say, Uday, to answer your question, if I say that the force F is 50 newtons towards north or towards northwest or whatever, then it's correct, because on the left hand side you have a vector and on the right hand side of the equality you have given both the direction and magnitude, so it is fine. But if I just say the force F is 50 newtons, then that is wrong. Correct. In proper sentence, what I have to say is the magnitude of the force is 50 newtons, or in mathematical symbol, I'll show that mod of F vector is nothing but 50 newtons. Okay, so that's just a technical point only. All right, now the next thing, now we are coming to the really important part about from where our vector algebra will start, and that is geometrical representation of a vector. Now don't confuse representation with the symbols that we use, because symbols are basically about notation, how we notate that it's a vector quantity or is the magnitude of the vector. Representation is actually about how we, how we define the quantity, how we represent the information about the given quantity. So geometrical representation means we are going to use geometry to represent a vector such that, so it is basically a method whereby by which a vector, see E, is represented using a geometrical tool. And when we say it is represented, by that we mean that both its magnitude and direction have to be specified. Then only we can say that the vector is correctly represented. So it has to be represented such that both the information about magnitude and direction are given, but using what? Using a simple geometrical tool. And what is that geometrical tool? We'll understand that next. So in this, what we do is we represent a vector by drawing an arrow. Now the arrow has two important factors. One is the length of the arrow, because it's a fixed line segment, but it also has, what is the difference between a line and an arrow? A line has a fixed length, an arrow also has a fixed length, but the arrow also has a particular direction in which it is pointing. It is given by the arrow's head. Okay, so a vector, so geometrically, any vector can be represented by drawing an arrow. Okay. Now, how that arrow is going to help us as a tool, such that the two things. The first thing, the length of the arrow that length actually represents the magnitudes. And secondly, the direction in which the arrow head is pointing. So that points along the given vector's direction. So what we mean by a vector's direction is its line of action. Okay, so if it's a force, that means the force is acting along the direction in which I have drawn the arrow in. If it's a displacement, the displacement is pointing from initial to final position as per where the arrowhead is pointing. Okay? So this is what we use to represent a vector in geometrical method. The vector quantity, it's, think of it like this, that, for example, in statistics, you've seen that you can represent quantities using a bar graph or a pie chart or something. So there you're representing what kind of quantities? Only scalar quantities. So you just need one kind of information. So in a bar graph, for example, when you're drawing different quantities, like the population of different towns or the distances traveled by different people or things like that, if you're comparing them using a bar graph, the length of the bar is giving you information about just the magnitude. But there was no question about information about direction, because you were always dealing with scalar quantities. So let's say, you're comparing the mass of rice in 5 different bags using a bar graph. So bag A will be represented by a bar like this. Bag B will be represented by a smaller bar if it has less mass. Bag C might be have. So the length of the bar in each case is representing what? The mass of rice which is in that bag. So it's just representing a scalar quantity, because it's representing just magnitude. Similarly, if you use a pie chart, for example, it is the area of the different sectors which represent the magnitude of the different physical quantities. But here, it is not enough to just have magnitude. You have to have some kind of geometrical tool. Instead of the bar graph or the pie chart or whatever, we have to define a new kind of geometrical tool, which will give us both the things. It will give us information about the magnitude of the vector, as well as information about the direction of the vector. And by direction, I mean its line of action. So what we use is, instead of a line or a bar or a pie chart or something like that, we just draw an arrow. So the arrow has two geometrical properties which define it. One is the length of the arrow, and the other is the direction in which the arrow itself is pointing, the arrow head, whatever direction in which it is pointing. So each property of the arrow now represents each property of the vector itself. The length is giving you information about the magnitude of the vector, and the arrow's head points along the direction in which the vector acts. Okay, so hope this point is clear, and just make a quick note of this. So this is the geometrical representation of a vector. So in the geometrical representation, basically the method is about using some kind of a geometrical tool to represent the vector. And what we mean by represent a vector, that means it should give information about both the things, the magnitude of the vector as well as its direction. So this is how that happens. Okay, so if a line has arrows at its either ends, then can it represent a vector? No, such a line will not be used to represent a vector. So what we mean by an arrow is that in our language, an arrow has an origin and a head. Okay, so the origin of the arrow is where it starts from, and the head of the arrow is on the other side, is where it points. This is by definition for us an arrow. Okay. And from here to here, this is the so-called length of the arrow. Okay. And this point here is sometimes called the origin, or you can also call it the source of the arrow. And this point is called the head. Okay. Or you can also call it the tip of the arrow. Origin is sometimes also called tail. People also call this the tail of the arrow and the head of the arrow, like that. So that is a common nomenclature that we use for arrows. Okay. So let's understand this representation with an example. Okay. Yeah. So that is the whole point actually. I'll explain through this example. You'll understand how we understand the direction of the given vector. Okay. So suppose we have a situation like this, where we have actually started by drawing a coordinate frame like this, where this again as usual represents the east direction for us, and this represents the north. But again I'm saying as usual, but it doesn't mean it always has to be like this. This xy plane for us, or the axis that we have drawn, they could also be a vertical plane. It need not be a horizontal plane. So that is completely arbitrary how we are drawing it. Okay? But in our particular diagram here, it is like this. Okay. So now let us say that I have drawn some specific vectors, which now let's say look like this. One particular vector that I'm drawing is like this. This is now another vector that I'm drawing is, let us say like this. Okay. And yet another vector that I'm drawing is, let's say exactly like this. So now let me say that this vectors are denoted by these symbols A, B, and C. Now the given information to me is that the vectors are drawn to scale such that magnitude of the vector E is 25 newtons. Let's say they are force vectors. Okay. So find, first of all, magnitude of the vector B and magnitude of the vector C from this. If E's magnitude is 25 newtons and B and C also represent force in newtons. So given that the vectors are drawn to scale, the vectors E, B, and C are forces, okay, and they are drawn to scale, okay, such that E's magnitude is this much. Then we have to find this, okay, and we have to also find. So that's the first thing. Find the magnitude of B and C, and the second thing is we also have to find the angle between B and C and between A and C. Between A and B, you can see it's very obvious. It is just 90 degrees. So I'm just minimizing this a little bit so that you can understand. And also, express the directions of B and C using geographical directions. That is north, south, east, west. Using that, express the direction. Okay, so this is the question for you. Just try this out. So just try to think, that this is a perfect graph paper and I've drawn the vectors to scale. So make use of the boxes in my whiteboard sheet. Actually, just make use of the boxes to try and understand how I've done the drawing to scale. Okay, so I'm waiting for your answers for the first part, magnitude of B and C. So that's why I said magnitude of the vector is 25 newtons. Yes, Prince, it's correct. Divyam, very good, correct. Sneha, correct. Uday, correct. 75 नहीं होगा बेटा. Okay. अच्छा, firstly, I hope there's no confusion with my handwriting here. This is newtons. Okay, it's force. So the unit is. Okay. Now you can see over here that, if I am to, so let me just magnify this a lot for you. So suppose I just take one box like this, as having dimension L by L. So you can see L represents how much? Now remember, magnitude of A was 25 newtons. The magnitude of the vector E was 25 newtons, and this length is actually how much? You can see in the diagram, it is 5L. There are 5 boxes, 1, 2, 3, 4, 5. Okay? So that means 5L represents 25 newtons. Okay? So that means L represents how much? 5 newtons. Okay? Now likewise, when I think about B, this length of B from here to here is how much? It is 4L. So now 4L will represent how much? 5L was representing 25. So 4L will represent how much? 20 newtons. So from that I know that the magnitude of vector B should be 20 newtons. Okay? Now from this you can also understand that this diagonal length is L root 2. So here for C you can see what is the length of the vector C. The length of this arrow is actually 4 diagonals, 4 boxes ka diagonals. So it is 4 root 2 times L. That is the length of this arrow. So that means what should be magnitude of C? It should be 4 root 2 into 5 newtons. So it should be 20 root 2 newtons. Okay. So that is a concept. So I'll just explain this in detail. Okay. So assuming in my graph, a single square box has a dimension of L by L. Okay. So then we can see that since the length of A's arrow, that length is 5L. Okay, and mod A is given to us as 25 newtons. Therefore, we can see that our scale the scale used in the drawing is such that 5L represents 25 newtons of force, or L represents 5 newtons. Okay. Therefore, now from the diagram itself, you can see, from the drawing, you can see that B, the arrow was 4L. So therefore, magnitude of B becomes 20 newtons. And C, the arrow was, it is the diagonal of 4L by 4L square. Actually. If you think about it, if you go back to the diagram, so the arrow was 4 root 2 times L in length. So therefore, you can see that magnitude of the vector C is just becoming 4 root 2 times. Now that length represents 5. So it's representing 20 root 2, or approximately 28.2 newtons. Okay. So this is how we calculate the magnitudes of the vectors. Now see, this is just for representation purpose. We will actually never be doing calculations from the diagram. We'll be using things like trigonometry and Pythagoras theorem and various geometrical tools for actually getting the magnitudes. We won't be using we won't be sitting and counting boxes and all that, because we won't be using graph paper and all that. But this is just to show you the proper method of the representation. What I meant by saying that the arrow has the two aspects, the length and the direction, and how the length represents the magnitude of a vector, whereas the direction of the arrow head actually gives you the direction of the line of action of the vector. So you can see over here that A's vector, the head is pointing towards east. So that means that force that represents the vector A, the 25 Newton force, uska line of action kahan pe act kar raha hai? It is acting towards east. Whereas for the force B, its line of action is towards north. And for the force C, you can see that angle is 45, so it is actually towards northwest. So further, you can see the geographical directions of A, B, and C will become east, north, and northwest respectively. So that is your C part's answer. Okay, so hope all of you are clear with this. Now work out the second part, that what is the angle between the vector B and C, and what is the angle between the vectors A and C. Okay, so correct. The angle between A and C is 135 degrees. That's correct. We can also express it as 225, but we always take the smaller of the two. So yeah, I'll minimize it. So the answers of the first part, if you're noting down, is this. Now we'll come to the angles part. And to answer some of your questions, Prince and Anmol, etc., we can express the angle between A and C as, technically, if you look at it, we can express it as 135 or 225, but we always take the shorter route. So we write it as 135. Whereas the angle between B and C should be 45 degrees. Correct. Okay. So coming back to the diagram here, you can see that if I just use the same diagram to also now express the angles. So in this, you can see that this angle is suppose alpha. Okay. Then this angle is suppose beta, and then also this whole angle, this one, is gamma. So you can see that in my diagram, the angle between A and B you have not asked, but okay. So that one is actually nothing but alpha. It is the angle between the B vector, which was like this, and the E vector, which was like this. And the magnitudes are not important as far as this angle is concerned. This is my alpha, and that is equal to 90 degrees. Or you can also write it as pi by 2 in radians. Now, similarly, the angle between B and C, that one is nothing but gamma. And because C is, you can see it is perfectly bisecting that square. So you can understand that the angle between B and C will in fact be 45 degrees. This is the vector C. You can see that this angle is your beta, and that, sorry, not gamma, it is beta in my diagram. So that is 45 degrees, or pi by 2, sorry, pi by 4 radians. And finally, the angle between A and C. So for that, you have to understand that we are talking about this angle. This was my vector A in the diagram, and vector C in comparison was lying somewhere here. So this is the angle gamma that we are talking about, this angle. And that from the calculation there you can see is, because this angle is 45, so that is gamma, which is 180 minus 45, or 135 degrees, or you can also write it as 3 pi by 4 in radians. Okay. So this becomes the angles between each of the pairs. The conversion factor is that pi radians is equivalent to 180 degrees. And this comes from the fact that one full circle is 2 pi, and that represents 360. Rest is unitary method. Okay, so now finally in this you can also see that if you express the vectors geographically in this particular question, so also geographically speaking, the vector E, you can see it is a force of 25 newtons acting towards east. V was a force of 20 newtons, but acting towards north. And likewise, C in my diagram was a force of 20 root 2 newtons, but acting towards northwest. Because it was perfectly at 45 degrees, so we don't need to give any angle. It is 45 degrees north of west. So when we just say northwest, it's understood that that angle is 45 degrees. So we don't have to give a particular angle. So this is the geographical representation. Okay, so let's conclude this with a sort of reverse question on this, that now I'm giving you some information about directions and you have to actually draw the vector arrows. So in our next example, what we'll do is, let's say S1 represents a displacement of 10 kilometers towards east. Okay. And S2 represents a displacement of 30 root 2 kilometers towards northeast direction. Okay. Now you have to first of all draw vector arrows, and for that you can just draw a rough sketch. You don't have to do a graph paper kind of exact one, just a rough sketch to represent S1 and S2. And also find the magnitude of S1 plus S2. Yeah, people, sorry, I got logged out because there's an internet outage at my place. I've just come back online through my cellular network. So that is why my computer is not on screen and you're not getting the whiteboard. Yeah, Prince, actually that page and all is just stuck. Okay, just give me a moment. Okay, I'm trying to come back online. Yeah, just give me a minute. I should be able to come back. My connection seems to be working now. So just give me a minute. Let me. Okay, I'll give this one more try to try and log on again. Okay, so unfortunately, people, there seems to be an internet outage at my place. Okay, so what we'll do is, anyway, it's time up, so we'll conclude the lecture here. The last question which I put up on the whiteboard when I send you the the answer to it will actually become 50 beta, and I'll explain to you how it will become 50. But right now, unfortunately, I'm not able to draw the diagram, so I'm not able to show it to you. But I will send you the PDF notes of today's class notes, which will have the diagram in the end, which will explain how the answer for the last exercise problem will come out. Okay, so that S1, S2 displacement problem, don't worry about it right now. I will send it to you in the class notes, and next lecture when we start, we will start with the explanation of that one, and we'll carry forward vectors from there. Okay, so that's it for today's lecture, people. And hope you understood everything. Okay, I will also send you a list of things that you can read from the vectors booklet. You would have received the PDF of the first booklet of physics. You know, it's called Useful Mathematics of Physics. So if you have received that, you haven't received that yet, you will receive it very soon. Otherwise, I will forward it to you. So that is a printed PDF booklet which will have theory notes as well as problems in vectors. So I'll see to it that you receive that. So once you get that, I will also send you some instructions on what all pages you can read to revise today's lecture from that, apart from my whiteboard notes. And that's how you can prepare for the next lecture coming up. Okay, people. So that's it from my end today. Okay. God bless and stay safe till the lockdown lasts or whatever. Okay. Until next time.